So in this tutorial, I want to go over something called a buffer, which you'll come across, buffers quite a bit, when you're dealing with acids and bases. And buffers are just basically used to prevent the pH of a solution from changing too rapidly. And we'll actually go through that a little bit more. So basically, definition of a buffer is a solution that resists changes in pH when limited amounts of acid or base are added to it. So for example, if you were to add 0.01 moles of HCl to water, without any buffer, what basically happens is that you see a pH drop from 7 to 2, just by adding a little teeny tiny bit of HCl. But now, if we go and add that same amount to a buffer solution, we'll see that the decrease might only be by 0.1 instead of having it by the 5 that you see up here. So buffers can really go and make the changes in pH, very, very small. And just basically what makes up a buffer, it always contains an acid and a base species, and they're at equilibrium. You can either have a weak acid and a conjugate base, where if you have something like that, whenever a strong acid is added to this particular buffer, you'll begin to see the hydronium ions react with the base in the buffer. The other type that you might have is a weak base and a conjugate acid, so that if you add a strong base, what you begin to see is the hydroxide ions react with the acid in the buffer. So that's why you don't see a big change in pH, because of the fact that it's actually reacting with what's already in the solution itself. One thing that I want to point out is that when you use a buffer, it always has to be either a weak acid or a weak base. You can't use something that's strong, because something that's strong will never reach equilibrium because it's able to react completely. Some characteristics of a buffer, just basically first off is the buffer capacity, which is just basically the amount of acid or base that a buffer can react with before you see a significant change in pH. So you can't just continue to add an acid or add a base to a buffer, and have that change not happen. It is going to reach a point where you use up the buffer, and then that's it. You'll see a big change in pH. The other thing that you have to pay attention to is the pH of the buffer. You need to know what that is so that you're able to use the correct buffer, when you're dealing with a particular solution. And just to show you on a graph what a buffer looks like, in this case, you have on the y-axis just the pH. On the x-axis you see either the amount of H3O being added or the amount of OH being added. And you also notice that you have just this region right in the middle. That's showing you the small pH changes that are taking place. Usually with a pH, with a titration curve, which is what this is, you'll begin to see just a level slope, and then it suddenly goes and spikes, upward. When you have a solution with a buffer in it, though, you won't see that spike. You'll actually see a gradual incline happening until you reach the buffer capacity of that buffer. So let's just go through the calculation of how you would go about making a buffer. So in this case, you'll have, like I said, either an acid, weak acid, or weak base, depending on what you have. In this case, if you look at it, NH3 is a weak base, and then its conjugate is NH4Cl. So we're dealing with a basic buffer, instead of an acidic buffer. Now you want to know what the pH of this buffer is going to be, again, because of the fact that you want to plan accordingly to see if this buffer is going to be appropriate with what you're trying to do. So let's go through this. You'll notice that you have 60 milliliters of 0.1 molar NH3, and then you also have 40 milliliters of 0.1 NH4Cl, which again is its conjugate. So the first thing you need to know or figure out is just the total volume of this solution, because you are adding two solutions together, so you do need to have the total. So in this case, you had 0.060 liters of the NH3 plus the 0.040 liters of the NH4, so that's just going to form 0.1 liter, or if you were to change that over to milliliters, it'd be 100 milliliters that you'd have. So that's the total. Now though, we need to take that into account when we look at our molarities of our solutions, because it's not going to change it. It's not going to stay at 0.1 because of the fact that now we have more volume than what we started off with. So what we need to do is just take our 60 milliliters that we have and our 0.1 and just multiply them together. So 0.06 liters times 0.1 molarity, and you end up with 0.006 for the moles of that. Another way you can do this is just by basically putting it into the molarity equation. I'm just trying to skip a step a little bit, but that's just basically what I'm doing here. So then you have 0.040 liters, multiply that by the 0.1 NH4Cl, and you end up with 0.004 moles. So that's just basically going and figuring out how many moles you have if you had 60 milliliters and 40 milliliters. Now though, we need to take into account that we have 100 milliliters. So what we're basically going to do is just divide each one of those by 100, or by 0.1, because we have to deal with liters. So you had 0.006, divide that by 0.1, because again we want to find molarity again, but we want to find the molarity of 100 milliliters of the solution instead of just 60, let's say. So you have 0.006 over the 0.1, so you end up with 0.06 molar of NH3. Now, by coincidence, it does end up being the same as what you started off with. It's not always going to do that, though. That's just the numbers in this case, but it's not always going to end up being the same. And then do out the other one, 0.004 over 0.1, so you end up with 0.04 molar NH4Cl. So then you have that portion of it. Now, basically all you have to do is plug this all into an ICE equation. What you're assuming is that you have a base ionization taking place with the NH3. So you have NH3 coming together with H2O and forming NH4 plus OH minus. So now what you do is just go and fill in your ICE table as you did before. So in this case you'd have your NH3, your NH4 plus, and your OH minus. For NH3 you start off with 0.06, NH4 you start off with 0.04, and OH minus you didn't start off with anything, so it's 0. Now for the 0.06 and 0.04, those are the numbers that we had when we calculate everything out according to 100 milliliters. So it's not going all the way back to the beginning. It's going back to the calculation that we just did before. Now for your change, negative x, positive x, positive x, and then equilibrium would be 0.06 minus x, 0.04 plus x, and then x, like that. So now plug this into your equilibrium expression. So you end up with 1.8 times 10 to the negative 5 equals, you'd have NH4 plus, so you'd have 0.04, and then OH minus, which is your x, over 0.06. Solve for x, and you end up with 2.7 times 10 to the negative 5. That also equals your OH minus, as you can see from your ice table that you create up there, OH minus is just basically X. So from here you can find out your POH, by taking the negative log of this number. So your POH in this case would be 4.57, and to figure out your pH, just subtract this number from 14. So 14 minus 4.57 is 9.43, and that would be your pH for this buffer solution. Alright, so let's go on to the next example, where in this case you have 30 milliliters of 0.5 acetic acid, you have 70 milliliters of 0.2 sodium acetate, and now we're actually going to go and make this buffer using those using that data. So first thing you need to do is figure out your total. So total in this case are just the total values of the two volumes. So you have 30 milliliters here, you have 70 milliliters there, so add those together and you have 100 milliliters. And if you change that over to liters, you end up with 0.100 liters, like that. Now we need to go and figure out how many moles we have for this though, for each species. So you have 0.03 liters times 0.15, and that'll give you the moles of the acetic acid, which is 0.0045. That's the moles, but you want concentration, so then you just go and divide this by the 0.1, which the 0.1 that I'm talking about is right there, because we need to take into account the total volume. So you end up with 0.045 for the molarity for acetic acid, and then for the other one you have 0.07 times 0.20. That ends up being 0.014. Again, you need to divide this by the total amount of the solution, so divide that by 0.1, and you end up with 0.140 for that molarity of the sodium acetate. Now we just need to set up our ice table, so figure out your acid ionization equation first. So you have HC2H3O2 plus water yields the acetate ion, so C2H3O2 minus plus the H3O plus. Do out your ice table, so you end up with HC2H3O2, C2H3O2 minus, and H3O plus. Now, the initial values that we just calculated, you had 0.045, 0.140, and then 0 for that case. Now, if we were to do our equilibrium expression, Ka for this particular reaction is 1.7 times 10 to the negative 5, which you can look that up if you need to. 10 to the negative 5 equals the C2H3O2 minus, so 0.140 times X over 0.045. And as you can see, I didn't do out the full ice table, but by this point I think you know how to do that. So that's the reason why. That's where this X comes from as well, because of the fact that if you were to do out the change in the equilibrium, you would end up with H3O plus as an X. So that's where the X came from. So then go and solve for X. So you end up with 5.46 times 10 to the negative 6. This is already H3O plus, so now you can find the pH by just taking the negative log, and so the pH of the solution is 5.26. Now what I just showed you is the long way of figuring all this out. There is a shorter way of doing this as well. On the AP exam you might be required to do the long way, as opposed to the short way, so that's why I showed you that. But just to go over what this is, the Henderson-Hasselbalch equation is just another way of determining the pH of a buffer. where here's the equation where you have pH equal to pKa, where pKa is just basically the negative log of the Ka plus the log of